everyone.
Hello.
How are you today?
Good.
I'm good.
Good. Terrific. All right. Great to see you all. Anybody have any questions or anything fun to share?
No.
Anything new going on? All right. I have to, Josiah.
I have something cool I built out of Legos, but I have to go get it real fast.
Okay, real quick. I am looking here for Cheyenne. I'm not seeing Cheyenne. I kicked Cheyenne out last week. I closed the window and it made it impossible for him to come back in. So I'm keeping an eye out. Just help me watch. Let me go into. We'll have to wait just a second here. Go ahead, Josiah. Let's see it. Let me make you big enough, Josiah. We'll spotlight for everyone. All right, so now everybody should be able to see you bigger.
This is a helicopter, so you can see I have the battery pack and then remote control. And
wow. That's amazing. Very cool. Yeah, very well done.
And the blades actually generate, it can't fly, but it generates actually a lot of wind.
I love that. Yeah, like your own private fan there.
Mhm.
That's excellent. Thanks for showing us. That was a lot of fun. All right, let me check again. All right, I still don't see Cheyenne. Oh, okay, well, we'll keep hoping. He didn't write to me either, so wait just a second. A big class here today. Everybody's here. Wonderful. All right, so I learned that if somebody's computer freezes, their screen freezes, I can't delete them from it because then they won't be able to get out. So we'll just have to deal with that as we go. Okay. All right, sorry to take a minute here. Okay, let's go ahead and get started with our class, and I will keep an eye on the messages for here. Let me share my screen with you all. And let me know if you cannot see where it says physical science. All right, good. Everybody can see it. Open my chat box. Any questions? A Lego club, what a fun idea. Interesting idea. All right, let's go ahead and get started with our class tonight. So I did want to talk about a couple things that you guys had asked about in previous classes, give you a little bit more information. So let's hold our conversation now just to class, and then you can, we can talk about other things if there's time at the end. But it's when everybody talks, the text goes by too fast and I miss questions. Okay, so here we go. A couple of you, one of you, who asked me about dark matter? Was it one of you guys? Josiah? Yeah. Okay. So I wanted to give you some more detail about dark matter. Well, what I said was it's like nobody really knows, and that's the truth. It's this mysterious stuff that actually makes up more of space than anything else. We know it's there, but we can't really detect it. We can't see it. We can't touch it. It's invisible. It doesn't give off any light. It doesn't reflect any light like normal matter does, like stars and planets, and even you and me, we reflect light. So why do scientists think that dark matter exists in the first place? Well, because when they look at a galaxy, when they look at a huge group of stars, they notice that the stars, some of them, are moving way faster than they should be. So if the only matter in the galaxy was the stuff we can see, then the stars should be flying off into space in a uniform way, but they don't. That means there has to be some extra invisible stuff, which they call dark matter, that holds the galaxies together, keeps things from flying away from one another. It has to be some kind of gravity. So kind of a simple example for you about this is imagine that you've got a ball and it's tied to a string and you're spinning it around and around. Well, what keeps the ball from flying away is the string, right? You let go of the string, the ball flies off. Well, out in space, this dark matter is like that string. It's like the invisible string that keeps the stars from flying away into space as they move around in their galaxies. So we can't see it. We know it's there. It makes up about 85% of the universe. So it's pretty significant. The stuff that we see, like the stars and the planets, that's only a small part of the universe. And scientists are really still trying to figure it out. We know it's important, but we don't know what it's made of. It's really one of the biggest mysteries in science today, is what exactly is dark matter. So that's a little more detailed explanation of, it's kind of a mystery. Nobody's really sure what dark matter is. All right, and then last week, Wick, are you here? Is Wick here? I think it was Wick. I got to write down your names when you guys ask me questions. So Wick had asked me if you can make infinite oxygen in the lab. So I don't know, that might have been the other class. It actually might have been the Wednesday section, but I thought you guys might be interested in the answer anyway. So the question is, if, you know, we talked about atoms and how you've got in the sun, let's say in our star, the sun, you've got 2 hydrogen atoms. And when under tremendous heat, those hydrogen atoms slam into each other, they fuse and they create something that has 2 protons in the nucleus. Anybody know what that is? What element has 2 protons in the nucleus? Hydrogen has 1. Josiah.
Helium.
Helium. So we've got 1 hydrogen, 1 hydrogen. When they slam into each other and fuse, they create hydrogen. So the question then is, can we just make a whole bunch of oxygen? You know, could we make enough oxygen for, like, you know, on another planet, to be able to make a colony on another planet? So the answer is a little bit complicated. You know, the answer to that is really no, we can't make oxygen. We can't make any matter, right? Because we learned matter cannot be created or destroyed. That's the law of conservation of matter. So we can't create or make any kind of these elements. What we can do, though, is we can liberate oxygen from other molecules. So what do I mean when I say liberate? What does it mean to liberate oxygen from another kind of a molecule? Josiah.
It's kind of like you're breaking apart a compound like water. You can break apart the hydrogen and oxygen and take out the oxygen.
Exactly. Just like I could take one of the Lego pieces off of your helicopter. That would be liberating that piece from the helicopter. So when we liberate something, when we liberate a molecule, an atom from a molecule, we are making it free from the bonds that was holding it together. So that's what we call a decomposition reaction. We're decomposing this molecule. And it's a kind of a chemical reaction where one substance breaks down into simpler ones, like taking a large Lego structure and breaking it into smaller pieces. So we can do that in order to liberate oxygen. So there's a couple ways that we can do that. We can heat up a substance that's called potassium permanganate, and that breaks it apart and it releases oxygen in the form of gas, which we can then collect. We can also do an experiment where we can decompose hydrogen peroxide. Anybody know how you can do that? How can we decompose hydrogen peroxide into water and oxygen? Matt.
Don't you let it sit in the sun for a while?
Basically, you just let it sit. You don't even really need the sun. The sun will speed it up. But if you just let it sit and it's exposed to the air, it will break down. That's why hydrogen peroxide bottles are dark and they have to stay closed. If either it was clear and the light could get to it, or it was exposed to the air, either way, it would break down. So hydrogen peroxide isn't very stable. It wants to break down. When it's exposed to either air or heat or light, those all speed up that decomposition reaction. But we can also speed it up in the lab with a process that we call adding a catalyst. Anybody know what a catalyst is? Josiah.
Some sort of substance that is not reactive on its own, but when combined with another compound, it reacts.
Yeah, excellent. The way it reacts is to speed up the process. Almost always. A catalyst will make a process happen faster than it would happen otherwise. So an example of this would be if we had manganese dioxide, that's a catalyst. Just mixing a little manganese dioxide in with hydrogen peroxide will produce oxygen gas and water. Now, I want you guys to watch the reaction in this video. This is that chemical, that manganese dioxide and hydrogen peroxide. Here you go.
Wow!
Pretty cool reaction there, isn't it? Don't try this at home. Okay, here it is, slow down.
Wow!
There's the reaction. So let's take a look at that reaction here for a second, or the equation here. So we started with 2 water molecules, 2 H2O. H2 is water. This 2 at the beginning means we have 2 of them. Anybody know what the AQ stands for right there? Matthew.
I actually had a question about
Okay.
the reaction.
Go ahead.
So because it's reacting, is it hot? Like is the temperature hot? Is it just like a normal like room temperature, or is it like cold when
So
when
this
that
one-
reaction happens?
Yeah, it depends. It depends on what the reaction is. Some reactions pull in heat. So the reaction itself, the stuff in the tube gets hotter. Others release heat so that the air outside gets hotter. And the reaction, the liquid that's inside there gets colder. We'll learn about those. I'm going to ask you to hold that thought for a bit because both can happen or none can happen. There are some chemical reactions that don't either release heat or take in heat on enough of a level to be able to feel them. So we will get to that. Good question. And Mel, you're close with aqua. It's aqueous is what AQ stands for. That means water. So we've got 2 water molecules in the form of water. They're not ice, they're not gas, right? They're in a liquid form. Then we have our magnesium dioxide right there. That's Mn is magnesium. When you've got 2 O's, that's dioxide. So magnesium dioxide break down to produce 2, I'm sorry, this is hydrogen peroxide, not water. H2O2 is hydrogen peroxide. Breaks down to release 2 water molecules and 1 oxygen molecule, and the G means gas. It means gas. Yep. All right, so let's watch another one. You can do this one at home. This is actually kind of a cool experiment to do at home if you have these supplies, and it's real safe. So you can release the oxygen through what's called electrolysis reaction, where you're going to pass an electric current through the water, and that splits it into hydrogen and oxygen gases. So what you need in order to do this is a 9-volt battery. You got to have these 2 terminals. So you need a 9-volt battery. You need 2 metal thumbtacks. They're inside there, and this plastic cup and some water. So and 2 test tubes. You need 2 test tubes to catch the gas. So let's watch the video of this reaction.
In that small plastic container are 2 metal push pins, and they're inserted a distance that's between the positive and negative lead of the 9-volt battery.
So put them
So you just
exactly as
insert them
wide
in
as the
there
battery parts are.
and make sure that they're that distance apart, and that should be fine. In the container is going to be some water that has baking soda mixed into it. The baking soda in the water allows electricity to flow between the 2 metal tips of the push pins. And so now you set them on the leads, and the electricity can flow between the 2 push pins now. And so electricity is flowing through the water, and so that's enough energy to break apart the water, make it undergo a chemical reaction, so that the H2O gets broken apart into H2 and O2. It's going to be hydrogen gas and oxygen gas. And both gases are going to flow up through the test tubes, and one of the gases is going to be in one test tube and the other one's going to be in the other one. How do you know which one's which? Well, if you take a look at the amount of gas in each test tube, there's going to be twice as much hydrogen gas as oxygen gas. So you can see in the right test tube, you have twice as much hydrogen gas as oxygen gas. This is how experimenters first learn that the ratio of hydrogen atoms to oxygen atoms in water is 2 to 1. It's 2 to 1 ratio, thus H2O.
Yeah, so that's pretty cool. You can do that experiment at home. Now, the reason that he put the baking soda in there, pure water doesn't conduct electricity. There has to be something in the water. Now, in reality, there isn't any water found naturally on Earth that's pure. They have to make pure water in a laboratory to purify it. So there's always a little bit of something else mixed in there, but there might not be enough to make it conduct electricity in this experiment. So adding that little bit of baking soda makes it conduct more electricity. It's pretty cool. Okay. So that is what we call diatomic oxygen. So what we created in this experiment here at the top was an O2 molecule. It had two oxygen atoms that were bonded together. So can we liberate atomic oxygen? What's the difference? What do I mean by atomic oxygen? Matthew.
I don't have the answer. I was gonna ask a question.
Oh, okay. Go ahead with your question. We'll go on.
So I know I've heard of like, I know it's like not, you shouldn't do this. But I've heard of like electric fishing, where like people will put like some sort of thing that conducts electricity and will have it hooked up to a battery, so it'll kill the fish. Um, with that, if I take like even like I've seen metal like mesh nets that they use, and then they have it hooked up to like a battery and put it in the water to make like a field of like electrified water to kill the fish, would that cause that same reaction? Like if I put like it in a lake or something?
So I'm not gonna condone that kind of fishing. Although I don't know, who knows? Maybe it's more humane. I don't know. Yes, whenever you're running electricity through water, there's going to be some breakdown of the water molecules into oxygen and hydrogen. There's going to be a little bit of that. How much? I don't know. Whether you could capture it, I don't know. Yeah.
I was
Okay,
just more curious to know if
yeah.
it would like if the surface would just start like evaporating,
I
or
probably
like you'd be separating the molecules.
Yeah, I'm going to say it's probably not going to be noticeable. In fact, this experiment here, you wouldn't really notice any change on the surface of even that little cup of water. It's only because we're catching it. You'd see the bubbles in there, but not on the surface, only because we're catching it in the test tube that you can really see the difference there. Yeah, good. And Josiah, I don't recommend trying to create a little flame explosion with hydrogen. Hydrogen gas is highly flammable. So again, everybody don't try this at home. Maybe Josiah was in a lab somewhere. Incapacity, dangerous things. Yeah. Okay. So what do we call? What is atomic oxygen? We were talking about molecular oxygen. O2 is molecular. So what do you think atomic is?
Oh, 3,
Not 3.
4.
That would be ozone. Atomic is just one oxygen atom. One oxygen atom is called atomic oxygen. So it's one individual oxygen atom. Molecular is 2 oxygen atoms that are bonded together. So there are a couple ways that we can release oxygen in just O1, in just an O form without the O2. So one of those is an electric discharge. That's where you pass a current through oxygen gas, and it can, in addition to what we were doing, like similar to what we were doing with the water. If instead of water in that there was oxygen gas, O2, it can break those bonds and split them in half. Another one is ultraviolet light, so that will split apart an O2 molecule into 2 atomic oxygen molecules. And another way is with heat. Really high heat, temperatures above 2000 degrees Celsius can break that oxygen into atomic oxygen. All right, so let's move on now to our actual class for today. So, sorry, went too fast there. So the periodic table of the elements. So this week, you guys are learning in detail about the periodic table. Zane,
But are we gonna have time for Kahoot today?
I don't know if we will or not. It depends how quickly we get through the content. Yeah, we'll see. I
Okay.
always have one ready, but we'll see. All right, so we're going to learn about the periodic table. You guys are going to learn this week about how it was developed and how it's changed in recent years. So one of you guys in one of the classes asked me if those colors mean something. They do. We're going to learn about that today. We'll learn that there's 3 major groups of elements. There's metal, metalloid, and non-metal. And then within those groups, we can subdivide this periodic table down depending on how they behave. So we're going to spend some time today and for the next couple of live classes learning the periodic table. It is just that important, and it is so cool. It is really an ingenious construction. It does take a little bit of explaining, though. So we all want to make sure that we understand the periodic table, because that's what matter is. It's all those elements on the periodic table make up all the matter that we're going to be learning about. But first, let's do a couple of different jokes. There's one. What is a chemist's favorite food? Chemist's favorite food. Anybody know what the chemical abbreviation for sodium is? Zane?
NA.
Na. So a chemist's favorite food is tuna. All right. What is the best element? What is the best element? It is gold, because it's awesome. AU is the abbreviation for gold. All right. What do you do with a sick chemist? If you can't heal him and you can't cure him, you might as well bury him. All right. Yeah. All right. So let's talk about the periodic table now. Oh, go ahead, Mel.
I forgot it.
Okay, that's all right. Send it to me and I'll put it in.
Wait, I
next
got it
week.
now. Okay, I just remembered it. Okay, so what does a surprised chemist say?
I give up.
H2O.
I don't really get it.
H2O.
Oh, like H2O, like that? Okay. All right. So let's look at the periodic table now. Now, there's a lot of different versions of the periodic table out there. If you guys were to hold yours up, you'd probably hold up a bunch of different kinds. Now, this is one that shows what the different elements are used for. So let's zoom in. You can see right there, if we zoom in, it's kind of blurry, but strontium is used for fireworks, and titanium is used for aerospace. Vanadium is used for springs. Chromium is used in stainless steel. These are kind of fun, different tables that show what things are made of. I have a cool one. You can't really see it all that well because it's clear, but this was a gift that I got. I'm going to hold it up so you can, I'll put a piece of paper behind it. It's got little chunks of all the different kinds of anything that you can capture inside there. So deep inside the periodic table. I wish it showed up better. It just really doesn't. But there's chunks of it inside there. So
Wait, can you show it again?
let me get something here. I'll put it in front of this. That'll be a little bit better, I think, to be able to see that. But you can kind of see the pieces of things that are in there. Now, obviously, you can't put pieces of everything inside there, but they did their best to do as much as they can. So basically, what is the periodic table? Okay, when we narrow it down to its basic thing, it is a way to orderly arrange the elements in a way that's useful to us. Now, that leads us to, what do we mean by element? What is an element?
Oh.
Arhan.
It's the purest form of a specific substance. It cannot be broken down.
Very good. Very good. So if you have a box of copper atoms, you have the copper, you have the element copper. If you have one copper atom, you still have the element copper, right? If you've got a balloon full of helium, you have the element helium. But if you have one helium atom, you still have the element helium. It is a substance that cannot be broken down by chemical means. So elements are made of atoms that all have the same atomic number. If you've got helium and hydrogen together, it's no longer an element. You have to have just the one. Send this periodic table image through AIM. This one? Yeah, I'll do that. Let me make a note to myself.
Just has a lot of cool visuals and how to learn it. So
I will do that. I will do that. Okay. Yeah, I'll go ahead and mute it there. That's fine. Okay, so when we're looking at elements, what we're talking about are the individual kinds of atoms that are in the universe. So all these elements, either alone or combined with other elements, make up everything. They make up our body, our world, our sun, our entire universe. They make up our Earth. Anybody know what the most abundant element in Earth's crust is? What's the most common found in Earth's crust? Josiah.
I think it's either carbon or nitrogen.
It is neither. Good guess, though. I love it when you guys guess. Shows your thinking. Zane.
Hydrogen, because
It is
water.
not hydrogen.
Ah.
It is not. It's the other component of water. It is oxygen. The most abundant element in Earth's crust is oxygen. Almost half of Earth's crust is made up of oxygen. You can see here, hydrogen isn't a lot. You can see some of them right here. These are the ones that would be the most prevalent of all. Now, the periodic table arranges these in a way that gives us lots and lots and lots of information. So for example, we can predict with pretty good accuracy what the properties of an element are based on where it is on the periodic table. We can predict what other elements it will react with. So understanding the organization of this table will help you to know a lot about these individual elements. Now, I don't expect you guys to remember everything that we're talking about today. The things that are really important are in the lessons. You can take notes if you want to, but I just want you to have a general overview of how the periodic table is put together. What are the blank spots? These two right here? Know what you mean, Mel? They're this line here. And I'll explain that in just a minute. In fact, let me jump ahead to that and I'll show you now why it is arranged that way. These ones that are right here would be right here. But if we did it that way, this is what the periodic table would look like. They'd be in this space right here. And it's too small to fit on, I mean, too big to fit on a page. That makes the cells too small, so you can't really see them. So to fix that problem, they move them and put them into rows that are like this. And that just shows these go there. Good question. All right, so let's just quickly review what's inside a square on the periodic table. Sometimes it is called an element. Sometimes it is called a cell. They all mean basically one of these squares on the periodic table. So what's inside there? Often the atomic number is inside there. What does the atomic number tell us? Anybody else? All right, Josiah, go ahead.
The number of protons.
Number of protons, great. I see a couple of you guys typed it in there. It's a lot faster if you talk. You don't have to though. I'll try to keep an eye on the chat though. Yeah, it tells us how many protons there are. If it gets more protons, it's no longer hydrogen. All right, it also gives us the name of the element. This one is hydrogen. It gives us the symbol. That's the H right there. And it gives us the atomic mass. It may tell you the number of valence electrons, and it may tell you the state of matter at room temperature. They don't all, but sometimes that's what it might give you. Now, the atomic number tells us how many protons there are. No two elements have the same number of protons. Here's what I want you to understand. A proton is a proton is a proton. The proton of hydrogen is exactly the same as the proton of titanium. or copper or gold. They're all the same. It's just how many of them there are that makes the elements different from one another. Now, we also have atomic mass. So this is a helium atom that we have right here. Its atomic mass is 4.03. So we know that its atomic number, well, you tell me, what's the atomic number of helium? Put your fingers up. 2. Yeah, it is 2. We know that because there are 2 protons in its nucleus. So right here, either one of these, either the red or the blue, are the protons. Now, with regard to atomic mass, we have to remember that there are these things that are called isotopes. That means it could be an element, an atom that has more neutrons or fewer neutrons than needed. So we might have more of those neutrons in that nucleus or less of the neutrons. Neutrons don't matter for the way an element behaves, but they certainly matter for how much it weighs. So when we have isotopes, we will have an atomic number that has a decimal point. So we saw that with helium, it was, well, what was it? I forget. 4.003. Well, if you're just adding together protons and neutrons, it seems like it should be an even 4, doesn't it? But it's not. So an atomic mass number that has a decimal means that that atom has some isotopes, and they do the average of the number of neutrons. So if it's got 5 isotopes, they're going to average those 5 different isotopes in order to get that mass, the atomic mass number. Now we measure atomic mass in what's called AMU. That stands for atomic mass unit. 1 atomic mass unit equals the weight or the mass of 1 proton. So remember that a proton in a hydrogen atom on Earth is exactly the same as a proton in a hydrogen atom millions and millions of miles away in another star. They're exactly the same. And we talked last week about how electrons are really small. Well, think of it this way. A paperclip weighs about 1 gram. 1 gram is equal to this many atomic mass units. 6, I'm not even going to do it. I don't know what that number is, but 6 with all those zeros after it. So that's what 1 proton weighs. And 1 electron is 2,000 times smaller than that. So yeah, we're talking really, 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 really small. Yes, Mel, you can have elements that don't have, they wouldn't be an element anymore, though. Now they're going to be called an isotope if it loses all of its neutrons. Yeah. There you go, Josiah. 600 septillion. That is 600 septillion. And 1 gram, that's a paperclip right here. And electrons are 2,000 times smaller than that, than 600 septillions. Yeah. All right. So now we have the symbol. Every element has its own unique symbol. It is either 1 capital letter or a capital letter with 1 or 2 lowercase letters after it. And here are some common ones that we have. So some of these are different. We've already talked about sodium. So sodium comes from the Latin name that means soda. Natron is what it is. Gold's chemical symbol comes from the Latin word aurum, which means gold. Now silver is interesting. Find silver on there. What is silver's atomic symbol? Mel.
AG.
AG. Yeah, silver actually gave its name to a country. So when the Spaniards arrived in Argentina, they thought it was a rich source of silver. So they named it Argentina after silver. The AG was after silver. Now, it turned out not to be. It wasn't a rich source of silver, but the name stuck. They had used it for a while. All right. Now, you can see here that the periodic table of elements can be divided into 3 main categories. We've got the big category is metals. Those are in blue. The next biggest category is going to be non-metals. Those are green. And then we have the metalloids, which are in the middle. And they're kind of have some characteristics of the metals, some characteristics of the non-metals. So I want to talk about the metals first because there's so many more of them. So you guys probably already know what metals are. You know that metals are good conductors of heat, right? If you touch a hot car sitting out in the sun, that metal is going to conduct that heat right into your hand. Metals are also good conductors of electricity. we use copper in our wires in our home because it's a metal. It's a really good conductor of electricity. Metals are shiny. Metals are also ductile. Anybody know what that word means? What does ductile mean? Stretchy, but more than that. They can actually be stretched into wires. So really stretchy. Let's put very stretchy at the beginning of that. And then that's correct. So they can be stretched into very thin wires. Metals are also malleable. What does malleable mean? Josiah.
They can be like pushed and pulled and like made into different shapes very easily. If they're-
Good. Particularly thin sheets. They can be pounded, very thin. Think about something like aluminum foil, how that's pounded into a very thin sheet. And they have chemical properties that cause it to react in water in a way that causes corrosion. Corrosion, like you've seen things corrode and break down. All right, now let's look at non-metals. So they're almost the exact opposite. Basically, if you think of what a metal is, a non-metal is going to be the opposite of that. They don't conduct electricity. They don't conduct heat. They're not ductile. They're not malleable, meaning they can't be stretched into wires or pounded flat into different shapes. They're pretty brittle. They break pretty easily. Metals don't. They're not shiny like a metal. They're dull. And many of the non-metals are gases. So sulfur is an example of a non-metal. It is, dull. It is brittle. All right. Next, we have these metalloids. They're right in the middle. So metalloids, or you can think of the word oid meaning like, they're metal-like. They've got properties of metals and they have properties of non-metals. They can be shiny or they can be dull. There we go. They can conduct electricity, but not as well as metals do. They are ductile and malleable, but not quite as ductile and malleable as metals are. So here we look at having them again. So the metalloids are kind of like stair steps in between the metals here and the non-metals here. Now, the periodic table has more than just those three different ways to group things, though. These columns up and down, they tell us a lot. They mean a whole lot. So elements in the periodic table are grouped into these columns that we call families. And elements in families have similar properties. So you can remember that. Family, you've got similar properties to other members of your family. So do the elements on the periodic table. They're similar to the ones in the same column that they're in. Now, they're not identical, but they're similar to one another. So as an example, went too far. So as an example, lithium and sodium and potassium are all members of group 1. They're all over here. So they're all going to be soft, shiny, white metals. Another thing that all members of the same family have is the same number of valence electrons. What does that mean? What are valence electrons? Looking for somebody who hasn't answered yet. Anybody who hasn't answered yet want to try? Zane, go ahead.
Valence electrons are the electrons on the outer shell.
Exactly. They're the ones on the outside. They're the ones that react or not with other elements around them. So it's those valence electrons are really important in making molecules and then compounds and then all the things that the world is made of. So all the elements in a family are going to have the same number of valence electrons. These all have the same number of valence electrons. So do these right here. Now we're going to skip these in the middle because they're a little different. These here, these here, these here, all the way to here. These are unique, so we talk about them a little bit different than one another. Now, we've also got periods. So each horizontal row, each row going across this way is called a period. They are not like other elements that are in their same period. In fact, the properties can change a lot. The first element in a period is also is usually pretty reactive and solid, where the last element in a period is always an inactive gas. All of these are inactive gases. So they're very different as you move across the table. Now, notice that each of the vertical columns, the up and down, the families of the periodic table has a number above it. 1A, 2A, 3B, 4B, 5B, 6, 7, 8, all the way up to what are we looking at here? 8, 10, and 2, 20B. I can't really see that, sorry. But then we go back to A here, 3, 4, 5, 6, 7, and 8A right there. Now, these all the way down are known as families or groups, and they're arranged in these vertical groups because they share these properties with each other. So you guys tell me, what element is in group 1, period 1? Group, period. Josiah.
Hydrogen.
Hydrogen. What element is in group 2, period 4? You got it, James. Calcium. Calcium. Yeah, calcium is Ca. So group 2, this would be the group. Period 4 would be 1, 2, 3, 4. Group 2, period 4, right there. All right, let's make it a little harder. What about group 13, period 3? Aluminum, very good. Not gallium. So I can see why you would think that, because if you start here and count down, this is 1, 2, 3, but boron is in period 2. The first period only has hydrogen and helium in it. That's period 1. Period 2 has lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon in it. Yeah, it is a little bit tricky. It is a little bit tricky. You have to look at that. Yeah, so let's talk about the groups. Remember that groups are called families. Now, hydrogen is kind of in a world of its own. So hydrogen is on this periodic table because the way it is right up here, because it has very unique properties. It makes it stand alone. So it can either lose 1 electron or it can gain 1 electron, but usually we'll put it right here because it has 1 valence electron, like the rest of the ones here, but it's different in almost every other way. So it is in a class of its own. It is gas at room temperature. Remember, everything else in period 1 is solid and not and very reactive at room temperature. Matt.
So, with the fact that it only has 1 electron, is it possible for it to give instead of share an electron? Because I know it normally will share, but what would
that's
happen
not
if it give?
It's not true that it normally will share. Depending on what it is bonding with, sometimes atoms share, sometimes they give, sometimes they accept. Hydrogen can do either of those.
So, because we can't like destroy energy and everything, like what happens to the atom? Because it no longer will have electrons. And like what will happen then with the atom?
So it's still going to be an atom. It's just going to be an ion now. Remember, if an atom gives up an electron, it becomes a cation. It's positive now because it gave away an electron. If it gains an electron, it is now an anion. It is a negative atom called an ion or an anion. Yeah, it still exists. Nothing has happened to it. You know, maybe some of them, once they give something or once they give, generally keep this in mind. What atoms want to be is stable. I mean, we all do, don't we? We all want life to be stable, right? We don't want things reacting all the time around us. So we're going to look for environments that keep us stable. That's exactly what an atom is trying to do. It's trying to be stable. If it doesn't have the right number of valence electrons, it's not stable, so it's not happy. The only ones that have the right number all by themselves are these ones over here. These are the noble gases. They have 8 valence electrons. That's what atoms want. They want to have 8. Now there's a couple, when we're talking about hydrogen and helium, they're a little bit different because they're not going to have 8. This one's either going to give or accept. This one, you know, helium is stable right there. So it's got its happy number of electrons. That's called the octet rule. You'll read about that. All right, so let's back up here. Oh yeah, we did hydrogen. Okay, so let's look at this first group right here. So see hydrogen's a different color? That's because it's in a class by itself. So we're going to consider only just the ones that are red in the picture. That very first family or group is going to be called the alkali metals. You can see that on this periodic table right down here. They are alkali metals. Now they are lithium, sodium, potassium, rubidium, cesium, and francium. These are all soft, shiny, they melt at low temperatures, they're highly reactive metals, and they tarnish when they're exposed to air. Those are the alkali metals. So they are the most reactive of all the metals. So let's take a look at and they react violently with water, They are never found as free elements out in nature. They're always bonded with something else. Remember, they want to be stable. They're very unstable when they're by themselves. So they look for something to be able to bond with, and they find it out in nature. Arhan. You're muted, Arhan.
It was an old hand.
Oh, okay. Okay. All right. So I want you guys to watch this video of some of the alkali metals reacting with water.
So here I'm going to take the lithium and add that to the water. It's going to generate hydrogen gas and lithium hydroxide. So you're going to see a pink color develop here. And then you're going to see some smoke come off, and that's either lithium metal or that's lithium hydroxide coming off of there. Maybe a little bit of liquid water. But it's not as reactive as, say, sodium, so I'm going to put sodium into the next one. And the sodium is actually probably going to ignite. So you'll see some orange flame perhaps, or some sparks, or some shrapnel.
That one spark at the beginning.
And then the last one, I'm going to go ahead and put my 2 pieces of potassium in. That I've cut in half. So this is less potassium than the other 2 in terms of amount. You'll find that the reactivity is a little bit greater.
That's just water. So yeah, very, very reactive. The alkali metals. That would be family number 1. Arhan.
I have a question. Why did all the waters turn pink?
It's a chemical reaction that happens. There's probably a what do they call that? There's another chemical that would be in the water that would that would react to show it. Yeah,
Okay.
explosives. Yeah, yeah. So the next column or the next family or group. Remember, column, family, group. That all means the same thing. The up and down, the vertical lines. So the second one are alkaline earth metals. Now, they're called alkaline earth metals. They're never found uncombined in nature. They have 2 valence electrons. Remember the periodic table? 2. There's this 2 at the top. These all have 1 valence electron. These all have 2 valence electrons. So they're called alkaline earth metals because they are alkaline, meaning they're on a pH level. They're more toward the alkaline side and not acidic. And they occur naturally in the earth. So you can see the metals here. What we have: beryllium, magnesium, calcium, strontium, barium, and radium. Those are the column 2, group 2, family 2, alkaline earth metals. So those are orange in the periodic table. Okay, so remember, we had alkali metals. Now we have alkaline earth metals. Now let's jump to the next one. These, the ones that are in groups 3 to 12, we call these transition metals. Now they tend to have to be very strong, very dense. They have a high melting point and a high boiling point. They tend to be pretty colorful when they're combined with other things. They combine in a way that provides colorful compounds. So they're yellow here in the picture. Let's look at what they are right here. That's the transition metals. These include the metals you probably have heard of before. You've probably heard of copper, tin, zinc, iron, nickel, gold, and silver. Probably. Those are pretty common ones. Now, these transition metals are pretty good conductors of heat and electricity. And like I said, they usually form brightly colored compounds. So a lot of times those transition metals are used to create paint, to give us the pigments that are in different paints. So we have group 1, alkali metals. Group 2, alkaline earth metals. Groups 3 through 12 are going to be the transition metals. Now the rest of these are named, they're composed of the elements that are in just one family. And they're named, for the most part, according to what the one at the top is. So group 13, that's going to be right here. This is group 13. It is known as the boron group because boron's at the top. So what's in the boron group? Well, we've got boron, aluminum, gallium, indium, thallium, and I'm not going to show you these bigger ones. They're not found naturally in nature. It would be Utinium. Anyway, they have these elements in group 13 have a variety of different properties. So aluminum, that's one. You guys know aluminum. It's one of the most, it is the most common metal that we find on the earth, that we find on the crust of the earth. Gallium melts at below body temperature. So if you held a piece of gallium in your hand, it would melt. So there are some unique properties that those have as well. So right there, that would be, sorry, I got those ahead. Go over here. Okay, so here's what we have so far. We have our alkali metals, alkaline earth metals, transition metals, and now we have the rest of these up here. Let's look at the boron family. Boron family is named after the first element at the top of the group. So these have 3 valence electrons. 1, 2, these are different. We come over here to 3. So the family includes the most abundant metal in Earth's crust, which is aluminum. All right, now, if group 13 was the boron group, what do you think group 14 is called?
Carbon.
Carbon. Very good, Evan. Carbon group. Yep. So that's where the carbon group is found. Okay, that's fine. That's fine. So the carbon group. Oh, sorry, I got to go back here. That is where the carbon group is found. So it is known as the carbon group or the carbon family because carbon's at the top. And there are 5 elements or 6 elements that would be in this group. That would be all of these 3 right here would be in the group. And these all have 4 valence electrons. Now, carbon and silicon, you see their top here, they're the only non-metals in the group that can form bonds by sharing electrons. So the elements all react with chlorine to form different kind of compounds. Carbon is the only element that can react directly with hydrogen. So they're a little bit different from one another, but they have a lot of the same properties, all the ones in the carbon group. So what do you think group family in group 15 are? What's the name of these? We got our boron group, our carbon group. What are these? Yep, these are the nitrogen group. So right there is the nitrogen group. So it contains nitrogen and phosphorus and arsenic and antimony and bismuth. The first element in the group is called nitrogen. It is a non-metal. So phosphorus is also a non-metal. Arsenic and antimony are metalloids. Bismuth is a metal. Because remember, we have that stair-step effect. So they are a little bit different from one another. I'm going to go a little bit more quickly because we're running out of time here. No, we're definitely not doing a Kahoot today. We didn't even finish the thing. All right, so the next one that we have is going to be the oxygen group. So the oxygen group, those would include these. They have 6 valence electrons. So they need 2 more in order to have that octet, in order to have those 8. So these elements can be found in nature, both free and combined. So what do you think the next group is? What do you think this one is called? You would think, Josiah, I couldn't catch you with that one, could I? Yes, you would think they would be called the fluorine group because fluorine's at the top. That would be a good guess. but they're not. They're actually called halogens. So group 17 are the halogens. And they get that word from the Greek word halo, which means salt former. So they're called that because they react with metals to form compounds called salts, not just the table salt, but any other kind of salt. So fluorine is an example. Fluorine is going to react explosively with sodium to form sodium fluoride. How many valence electrons do the halogens have? They're going to have 7. They are in group 7A. They have 7 right there. Excellent. And then our final category that we have here, the very last family, are called the noble gases. Yeah, they are noble gases. So they are colorless, odorless. They don't want to react with anybody. They have all 8 of their valence electrons. They're completely happy. They are very stable. They have a full outer shell. They don't want to form bonds because they're already happy the way they are. So they are, because they don't react with other things, we call them inert. So the noble gases are inert, meaning they don't react with other things in the atmosphere. Now, there are small amounts of all of these noble gases in the atmosphere itself, and we are out of time for today. So we will pick this up right where we left off for next week. All right. Everybody have a great week. I'll see you next time.
Bye.
Thanks for coming. Bye.
Thank you.
Bye.
Bye.